Welcome to Study Loop.
So in this problem we have the nitrogen gas in a cylinder with a piston, and this gas, which can be treated as an ideal gas, is going through a series of processes. And we're supposed to name and plot these processes on the PV diagram. So first process is the isobaric compression. So the gas is getting compressed under a constant pressure. So what happens is that its volume is going to be reduced by a half, but the pressure will not change. So we can say that the pressure is here. This is this constant pressure for this first part of the process, and this is 1.8 times 10 to the fifth power pascals. And in this case, we also have some volume V0 here, and we have some volume that is half of it, so V0 over 2. And the first point is the point A, and from the point A, it goes to the point B in a straight line. Like this. Next, we have expansion, but adiabatic expansion, so it will go back to V0 from V0 half, but the pressure will drop, so for a whole order of magnitude. And so we can say that the pressure is here. This is the second lower pressure, and it is going to be 6.82 times 10 to the fourth power pascals, and their common point is going to be here. This is the point C, and this is adiabatic process, so it goes like this. An adiabatic curve in this direction from B to C. And then we have an isochoric heating from C to A. This means that the volume will not change, but the pressure will increase due to continual addition of the heating energy. And it goes like a straight line here. So these are the three processes in this problem, and the sketch, PV sketch for each of them is for the part A of the problem, and therefore the part A of the problem is solved. So we can move to the part B of the problem. For the part B, we need to find the temperature T2 and the temperature T3. So the temperature T2 is the temperature at the beginning of the adiabatic expansion, and the temperature T3 is the temperature at the end of the expansion. So this is going to be between point B or state B and state C on the PV diagram. So to find T2, we will use the process from A to B. And since this process is a isobaric process, then we know that we can use this ratio here, which is derived from the ideal gas equation. And from here we can derive the temperature T2 equals T1 V2 over V1, which is 300 kelvins times the ratio of V0 half over V0. This will cancel out, and this turns out to be 1/2 of the 300. So T2 equals 150 kelvins. Next, to obtain the temperature T3, since this is the temperature at the end of the adiabatic expansion, we need to use the adiabatic formula. So the relationship between volume and temperatures for the adiabatic process is given by this equation here, on gamma minus 1 equals T3 V3 gamma minus 1. And from here we can derive that T3 equals T2 V2 over V3 gamma minus 1. Like in previous case, we will directly evaluate it 300 kelvins times, and it will be, in this case, V0 over 2 over V0. This will cancel out. Remember that V3 is equal to V1. So, and in the exponent we have 1.4 minus 1. So when we put these values into a calculator, we obtain that T3 for this part of the process equals 113.68 kelvins, or approximately 114 kelvins. And this part of the problem is done. So we can move to the part C. Here we need to find the minimum pressure, which can be obtained from the relationship that the ratio of minimum pressure and minimum temperature is equal to the ratio of maximum pressure over maximum temperature. This is derived from the ideal gas equation in the case of isochoric or constant volume heating. So Pmax or Tmax is equal to P minimum over T min. And from here we know that we can derive the minimum. We actually know the minimum temperature. So the minimum temperature is the temperature T3 that we already evaluated. And we also know the rest of the values. So we can immediately say that P minimum equals P max times the ratio of the temperatures, minimum over T maximum. And when we substitute the known values, we say and obtain that it is 1.8 times 10 to the 5th power, this is going to be in pascals, times 114 over 300, and the whole expression is in dimensions of pascals. Finally, when we put these values into a calculator and when we evaluate them, we obtain that P minimum is equal to 6.84 times 10 to the 4th power pascals. I plotted this on the first PV diagram, as you can see, because I already evaluated it, but it doesn't change the validity of the part A for this problem. So we have solved all parts of the problem. I hope you find this helpful, and I hope to see you in another lesson.